Welcome, this is Dr. Plague, and today I want to talk a little about running AVR microcontrollers at 20 MHz using a crystal. In an upcoming video, I will be presenting an example which just happens to contain an AVR microcontroller running at 20 MHz. So I thought it would be appropriate to explain how to set up an AVR for 20 MHz before that video comes out. This video is meant for those who do not know how to set up an AVR microcontroller to run at 20 MHz. So today I'll be going through the few settings along with some tips to successfully connect a crystal up to an AVR microcontroller. The microcontroller that I'll be using today is the DIP version of the ATmega 1284, but this video should be relevant to most other AVR microcontrollers too. So the first thing we should do is take a look at the electrical characteristics in the datasheet, and you can see that if we are running the AVR at 20 MHz, then we should be using a supply voltage from about 4.5 volts to 5.5 volts. Now we need to decide how we're going to supply that voltage to the microcontroller. But first, let's build this microcontroller circuit on a breadboard. And here it is, built up on the breadboard. Now, if we look at the schematic, you'll notice that we have 5 volts and ground throughout. On the breadboard, I've used the top and bottom power buses marked as plus and minus as 5 volts and ground. Now the question is, how do we introduce 5 volts to this breadboard? One obvious way is to connect a bench power supply directly to the supply rails. If you do this, you will want to be careful. Not all bench supplies are created equal. I'm using a 4-channel linear supply from GW Instech, set up to output 5 volts. It's a good idea to observe the power-up voltage curve on an oscilloscope. What we're looking for is a nice monotonic curve with no overshoot. By monotonic, I mean a constantly increasing curve that's not shaking all over the place. We would like the power-up to be less than 65 milliseconds. Let's capture the power-up trace of this supply on the oscilloscope. Okay, that's looking pretty nice. Notice how it comes up nice and smooth and reaches 5 volts with no overshoot. It reaches 5 volts within about 60 milliseconds. This looks very nice, and in my book, it is an acceptable way to power up the microcontroller. One thing you will want to do, though, is make sure you have some good capacitance on the supply rails, especially when you're using long supply leads like these. I find that 4.7 or maybe 10 microfarads usually does the trick. If you skip this, you may see some unpredictable behavior from your microcontroller, so make sure your supply is clean. I'm going to demonstrate one more bench power supply. I'll be using this here switching power supply to show you what you don't want to see. I have it adjusted to 5 volts. Let's turn on the supply and observe the output on the oscilloscope. You can see that this supply comes up much quicker, but look at this here. It overshoots before settling down to 5 volts. It looks like it's getting up to maybe 6 volts or so, but it's possibly getting a little above that. If we look at the absolute maximum ratings in the datasheet, you'll see that we need to keep the operating voltage at or under 6 volts. So for me, this bench supply is not a good choice for directly powering these microcontrollers. Yes, they will probably survive a quick transient, but I wouldn't recommend this supply. Another option is to use a regulator or DC to DC converter, such as a 7805 or something equivalent. I like to use these here DC to DC converters by Murata, the Oki 78 SR series 5-volt version. They are drop-in replacements for the 7805 linear regulators. I connect them up like this. Let's take a look at the power-up of this on the scope. We power them with 7 to 36 volts, and they come up quick with no overshoot. It doesn't matter which bench supply I use to power the DC to DC converter. Now, you'll notice that I've connected a 20 MHz crystal up to pins 12 and 13 of the microcontroller. You'll also notice that I'm using 20 picofarad capacitors here. Where did I get this value from? If we look at figure 9-2 in the datasheet, we can see the crystal with capacitors C1 and C2. Now, in table 9-5, we can see that for a frequency range from 0.4 to 20 MHz, it is recommended to use 12 through 22 picofarads for C1 and C2. Hence, I just chose 20. If you're ambitious, you can check the crystal datasheet to figure out what value of load capacitors to use, but I'll just use a recommended value. Also, since I'm building this on a breadboard, we can't expect the values to be too accurate anyway. Next, we're going to take a look at the fuse settings. Let's connect up the programmer to the programming header and go to Atmel Studio. I'll create a new project and just call it Blinker, since we will blink the LED that's on the breadboard. I'll just go into Device Programming and select the Atmel ICE. Now I'll supply power to the board and read the device signature. That worked, so I'll click on Fuses. This is the default fuse settings for a new unprogrammed AT-Mega 1284. Let's take a look at what we have. The first thing we have is the BOD level, and that's just for setting a brownout level detector which will reset the microcontroller. I usually set it to 4.3 when I'm using a 5-volt supply, but I'll just leave it as is for now to save on current consumption. Next, we have the OCD Enable, which is the on-chip debug system. I'll leave that unchecked. Then we have the JTAG Enable, and I don't need that, so I'll uncheck it. The next one is SPI Enable, and since I'm using the SPI bus to program this microcontroller, I'll leave that checked. Then we have Watchdog Timer On, and I'm not going to use that, so I'll leave it unchecked. Next, we have E2 Save, and that is to preserve the contents of the E2 memory during an erase. And I don't care about that, so I'll leave it as is. Then we have the Boot Size Fuse, and since I'm not using any bootloader, I'll just leave it as is. Then we have the Boot Reset Vector Fuse, and again, I'm not using bootloader, so I'll just leave it. Now we get to some interesting stuff. The clock divide by 8. This divide by 8, well, it can affect the frequency that the microcontroller operates at, but it doesn't have to. I'll explain that more later and uncheck it for now. Then we have the clock out fuse. Setting this will allow the clock signal to be output on port B1, which is pin 2 on the DIP package. I'll go ahead and check that so we can place a scope probe on port B1 at any time to see the actual clock frequency for the microcontroller. Finally, we have the startup time and clock select setting, of which we have several selections in the pull-down. These are undoubtedly the most important fuse settings to be able to operate at 20 MHz, so I'll spend the most time on them. First, we need to figure out which device clocking option to use, and we can see in Table 9-1 that there are 6 options to choose from. We can eliminate the low-frequency crystal oscillator since we know we're trying to operate at the highest frequency the microcontroller supports. We don't want to use any of the internal RC oscillators since we have an external crystal. We're not using an external clock, so we can eliminate that. We're left with 2 options: low-power crystal oscillator and full-swing crystal oscillator. But what is the difference between the two? Well, before we talk about that, let's take a look at Table 9-3 and notice that the low-power crystal oscillator is recommended up to 16 MHz. So that kind of eliminates the low-power crystal oscillator option. And we're now down to just one option, the full-swing crystal oscillator. Looking back to Table 9-5 shows the full swing option usable from 0.4 up to 20 MHz. Perfect! But what does full swing mean? Let me program the fuses to full swing, and let's take a look at a crystal pin on the oscilloscope. You will notice that the amplitude is fairly large. Not the full 5 volts of the supply, but around maybe 3.5 volts. The crystal is swinging from around 0.5 volts up to about 4 volts. In other words, it's swinging almost the full 5 volts. And let's look at a 12 MHz crystal now. You'll see that it swings even further, from close to 0 volts up to about 4.5 volts. Well, this is full swing. We're trying to swing the full 5 volts, even though we don't quite make it. And you could see that as the frequency goes up, the amplitude starts rolling off. Now let's program the fuses for a low-power crystal oscillator. And look at how low the amplitude now is. And we could try running a 20 megahertz crystal in this low power mode. And it does appear to work, but in my experience, the operation is very flaky, so don't do it. If we zoom in and compare the low power at 12 and 20 megahertz, you can see the amplitude is lower for the 20 megahertz. Therefore, we want to use full swing mode when operating above 16 megahertz. Now, we need to determine the startup time and additional delay from reset. If we look at table 9-6, we can see that the first 5 options are reserved for ceramic resonators. We're left with 3 options, and the only difference is the additional delay from reset. Remember I showed that it took about 60 milliseconds for my linear bench supply to get up to 5 volts? Because of this, I'm going to choose the option with 65 milliseconds of additional delay. So I've narrowed it down to this one choice from the pull-down. You'll notice that the fuse registers for extended, high, and low are FF, D9, and B7 respectively. Normally, I wouldn't have the clock out programmed, so the low fuse register would be F7. If we want, we could just edit these values directly and not worry about the settings above. So I'll go ahead and program the fuses with the clock out set. So now let's test this out quick. I'll write some code to blink the LED on port B0 once a second, or in other words, 1 Hertz. I'll set the data direction register for port B pin 0 as an output. Then, in an infinite loop, I'll just set pin B0 to 1, which will toggle B0. Now, in order to add a delay, I'm going to include the delay header file. And it needs to know the frequency of the CPU. So I'll define it as 20 megahertz. Now I'll add a delay of 500 milliseconds. And after programming the microcontroller, the LED does indeed blink once a second. Now, remember I said that the divide by 8 fuse doesn't have to change the operating frequency? Let's go ahead and set the divide by 8 fuse, and we would expect the LED to blink at 1/8 the speed. But look at that! It's still blinking once a second. What's going on? Let's look at the clock output on pin 2. We would expect it to be 1/8 of 20 megahertz, or about 2.5 megahertz. But the scope is showing a frequency of about 20 megahertz, as though we didn't set the divide by 8 fuse. How can this be? Well, truth be told, I left out some footage where I added some code into the project. Let me show you what I added. First, I checked the clock prescaler register. You can see in table 9-16 that we can add a division factor from 1 to 256 in powers of 2. When we select the divide by 8 fuse setting, we are essentially choosing a clock division factor of 8, but we can change this at runtime. So, if we have anything other than a clock division factor of 1, then I change it back to 1. To change the clock division factor, we need to first set the clock prescaler change enable. You can read more about this in the datasheet if desired. One thing I always do before changing the clock division factor is to add about a 1-second delay before doing so. That way, when you program the microcontroller, it doesn't try to change frequencies during the process. I divide 1000 milliseconds by 8 because the microcontroller is actually operating at 1/8 the frequency at the time, so I adjust for that. If we check the clock output pin on the scope and capture it within the first second of operation, we can see that it indeed is 2.5 megahertz before it switches to 20 megahertz. So, this is one way that we can make sure that our code runs at the correct frequency no matter how someone sets the divide by 8 fuse bit. Well, that's all I have for today. Hopefully everyone can get their AVR microcontrollers operating successfully at 20 megahertz. Thanks for watching, and I'll see you next time, right here on Dr. Play.